All right, let's move along to talking about what we call double angle formulas. So double angle formulas are ways of rewriting trigonometric functions that are sine, cosine, or tangent evaluated at twice some angle. And fortunately for us, there are some nice and easy formulas that we can use to quickly evaluate or verify or solve functions that involve using twice an angle or a double angle. And these are actually fairly easy to derive if you take, for example, sine of 2 theta, and the key to this is just to rewrite sine of 2 theta as sine of, think about what 2 theta means. It means you're taking theta plus some other thing, angle theta. And we previously already talked about sum and difference formulas. So see if you can actually derive these double angle formulas using the sum and difference formulas. All right, so if you had a chance to work through them, we can say sine of theta plus theta. This is equivalent to sine of the first angle times the cosine of the other angle, which just happens to also be theta, plus sine of that second angle times cosine of that second angle. And if you look at this carefully, this is just sine theta, cosine theta, plus another version of itself, or plus another sine theta, cosine theta. So this just comes out to be 2 sine theta, cosine theta. Okay, so we can say that sine 2 theta is equivalent to 2 sine theta cosine theta. All right? Okay, let's try another one. What about cosine of 2 theta? Take a moment and see if you can derive those. Well, cosine of 2 theta, again, is theta plus theta. And if we use the sum formula for cosine, we'd write this as cosine of theta times cosine of the other theta, not plus, but minus sine theta cosine theta. Oh, sorry, sine theta, apologize. And we can simplify this. Cosine theta times itself is cosine squared theta minus sine theta multiplied by itself is sine squared theta. So we can say, oops, I don't want to draw a line here. Let's just go ahead and do this. We can say that cosine 2 theta is equivalent to cosine squared theta minus sine squared theta. Now, if you think about this for a second, we can replace cosine squared theta with, we can write this as the following. We could say cosine squared theta is the same thing as 1 minus sine squared theta minus this sine squared theta that was already in there. So this would be equivalent to 1 minus 2 sine squared theta. So this is equivalent as well. This is another form of the double angle identity for cosine. And in the same way, you could also replace this sine squared theta that was originally in our substitution. We can say cosine squared theta minus, instead of sine squared theta, we can write 1 minus cosine squared theta. And this would be equivalent to 2 cosine squared theta minus 1. So depending on the scenario, you may want to do any one of these three substitutions for cosine of 2 theta. Okay? All right, now finally, let's go ahead and do tangent of 2 theta. Again, using the sum formula. Hopefully you get the picture by now. We can just say that this would be tangent theta plus tangent theta all over 1 minus tangent theta times tangent theta. This is just, again, the sum formula for tangent, which would then rewrite as, oops, yeah, that was right, 2 tangent theta all over 1 minus tangent squared theta, okay? So these are our double angle formulas, and these are just formulas that help us express trigonometric functions of a multiple angle or a double angle in terms of a single angle. And you can already see that this would have some uses when we're trying to do things like solving equations or verify, or anytime we need to rewrite a trigonometric function. So the types of problems we're about to do are going to be pretty much the same line of questioning that we've had so far in this chapter. We're just using some double angles through them. So let's work through a couple of practice problems. Let's start by solving an equation here. So let's try this one here. So we're going to rewrite cosine of 2x using the double angle formula. And if you recall, there are three different options that we had here with cosine of 2x. Well, what would make the most sense here? Well, hopefully we see that cosine of 2x can be rewritten as 2 cosine squared x. And can we see why that would make the most sense? Well, the rest of the equation is written in terms of cosine, so it makes the most sense to rewrite cosine of 2x just strictly using cosine. This allows us to simplify this as 2 cosine squared x plus 3 cosine x, and we can combine our constants and write this plus 1 is equal to 0. 2 cosine x plus 1 times cosine x plus 1 is equivalent. This is just me factoring. Then we can say cosine of x is equal to negative 1/2, and cosine x is equal to negative 1. Now we're just going to finish solving by figuring out which angles result in negative 1/2 when we take the cosine of them. So we've got 2 pi over 3, 4 pi over 3, and pi as well. Okay, so let's just go ahead and box those, and we're good to go. All right. Okay, go ahead and pause the video and see if you can work through this problem now. Well, at first glance, this might have been a little tricky because you might be thinking, okay, well, there's no way for me to rewrite 4 sine x cosine x. I don't have any identity that starts with a 4. But if you actually rewrite that 4 as 2 times 2, or that is to say 2 times 2 sine x cosine x is equal to root 2, now we can actually do that substitution. We identify that this here is equivalent to sine of 2x. So we have 2 times sine of 2x is equal to root 2. We can divide both sides by 2 now. Sine of 2x is equal to root 2 over 2. And you could try to do the substitution right now, or you can kind of solve this the way that we had done previously, which probably makes the most sense here. Okay, so we're actually thinking of what values, if we said let theta be equal to 2x, we can say sine of theta is equal to root 2 over 2, which means theta is equal to pi over 4 plus all of its coterminal angles. And then we can replace that theta with what we said theta was equal to 2x. And then we say x is equal to pi over 8 plus pi n. And we're going to do the same thing over here with the other place where sine is equal to root 2 over 2. We'd say sine of theta is equal to here 3 pi over 4 plus 2 pi n. So 2x is equal to 3 pi over 8 plus pi n. When we divide everything by 2, let me write that power pi n. And those angles would be x is equal to, so now that I have the two general solutions, I can just go through and plug in values for n, and I should get pi over 8, 9 pi over 8, 3 pi over 8, and 11 pi over 8. Okay. All right. Let's do an evaluating problem using our double angles, and I'll do one and give you some time to try the other ones on your own. Okay, so let me actually just zoom in on this. Just trying to find the right window here. Okay. All right. So let's use our double angle formulas to evaluate some trig functions here. First off, if we're saying that the cosecant of x is equal to 3, we can also rewrite this as using the reciprocal identity to say sine of x is equal to 1/3. Now, x is not an angle that we're accustomed to working with in the unit circle, but based on this, we do know that it is in quadrant 2. So I can sketch this angle here and its appropriate right triangle, its corresponding right triangle. I can say this is my angle x, and I know that taking the sine of angle x results in opposite over hypotenuse being 1 over 3. So just using the Pythagorean theorem, I can then say this adjacent side is negative 2 root 2. So sine of 2x then is what we're going to try to find using this triangle I've just sketched. Well, we know that sine of 2x, let me move this over here, sine of 2x is equal to 2 sine x cosine x. Well, what is sine here based on what we've just sketched? Sine of x is, well, that's given to us, 1 over 3. Cosine of x is negative 2 root 2 all over 3. And if we simplify all this, we get negative 4 root 2 over 9. Okay? Now see if you can use the double angle formulas for cosine and tangent. And yes, know that no matter which formula you use for cosine, you should still get the same thing. All right? Okay, and let's just do one quick verifying problem just to finish off this lesson. Let's verify the following identity here. So in the numerator, I'm going to use the cosine, I'm going to rewrite cosine of 2x. Let me actually just change my color here. Cosine of 2x as, and there are a couple of options, but I'm going to go with 2 cosine squared x minus 1. And the main reason why I'm choosing that is because I know that cotangent here is equivalent to cosine over sine. So that kind of gives me some guidance that I want my numerator to be in terms of cosine. Now, what about my denominator? Let's highlight that in green. Well, my denominator really, there's only one thing that I can replace this with. This would be 2 sine x cosine x. Okay, and let's do some simplifying and see where this takes us. Remember, we want this to be equal to cotangent of x. Well, I've got 2 cosine squared x. This negative 1 and this positive 1, those are going to negate one another. And if we do some dividing here, you can see that these 2's are going to divide out. I can divide out this cosine in the denominator with one of the cosines up here. And this leaves me with cosine x over sine x, which means I'm very close to just being able to say cotangent of x is indeed equal to cotangent of x. And there's my verification. And you can go ahead and try this next verifying problem on your own. Go ahead and check your solutions with what we have up on the website.